So welcome back and good morning. And today we'll see another type of galvanometer. So already we have seen two types of galvanometers. One was the D-Arsenal type and the other was the flux meter. And today we'll see the ballistic galvanometer, whose application we have already seen while we discussed about the experiment to plot BH curve as well as hysteresis loop. There we use the ballistic galvanometer in the circuit of search coil just to know the change in flux linkages due to changes in EMF induced so that was application of ballistic galvanometer. So ballistic galvanometer is used in magnetic measurements just to know the change in flux or change in flux linkages. So so basically we know that for any galvanometer there are four operating torques, that is operating torques or operating force. It is more appropriate to say it as operating torque. And the four torques are the driving torque, then the moment of inertia torque, the controlling torque, and the damping torque. So we know the equation for motion also. We'll come to that a little bit later. So what is the difference between a D'Arsenal type galvanometer and a ballistic galvanometer? The thing is that in a ballistic galvanometer, the moment of inertia is considerably large. The moment of inertia is considerably large. That is one difference. And the other difference is that the damping torque and the controlling torque are very small or negligibly small, or we can even consider that as zero. So damping torque as well as the controlling torque are zero, considered as zero, or we can say that the spring constant K as well as the damping constant D are zero or absent. So those torques are absent. So these are the major differences. So how that is made, so how such effects are made in this ballistic galvanometer, how such changes are implemented inside a ballistic galvanometer. For that, for maintaining zero controlling torque, we don't have any control springs. That is one thing. The other is that whatever be the connections, that connections are made by very loose connections, very loose helices, or by the use of loose helices, so that they don't impart any tension at any point. That is one thing. And the damping torque is avoided having having that is there are they are actually, the moving coil is wound over, that is air core, so that you can just avoid the damping effect. That is why the similar construction was there for the flux meter also. That is why we told that flux meter is another type of ballistic galvanometer. So in a ballistic galvanometer, we don't have or negligible damping torque as well as controlling torque, but we have considerable moment of inertia torque. And how does that be implemented in this ballistic galvanometer? For that, we attach small weights in the moving system, so that it has considerable moment of inertia. So moment of inertia means that it is very hard to rotate. So when that is not rotating, or when the theta is zero, when there is no change in deflection, or when the point is stationary, even if there is a change in flux, it is very hard to move or rotate the moving part. But when it starts rotating, or when it starts deflecting, or when it starts to deflect, it is very hard to, the swing of that motion, or that swing is very hard to stop as well. Or there will be oscillations, which is a damped one, but that oscillations will take time to die out. That is one thing. So one thing you can see that from my earlier statements, that it is not the pointer, it is the pointer will not be showing a steady state deflection, but when there is a change in flux, after that change in flux has happened. Why that happens after the change in flux has happened? Because of the large moment of inertia. So due to that, there will be a very large swing at first. Then that swing will continue, but the continuing swings will have lesser amplitude than the first swing, and considerably after some time, or maybe up to after 10 to 15 seconds, these may die out. Okay, so that swing or throw of the galvanometer, the first swing or first throw of the galvanometer is very important, and that is what reflects the change in flux, and that is what we want to note. That is one thing. So these are the things we have to remember as an introduction. So construction wise, these are the things you can read from the materials that I am circulating. And then we come to the theory part. As I have discussed, these are the four torques, that is deflecting torque, which is given by Td is equal to Gi. Gi is the galvanometer constant, where G is nothing but BAN. B is the flux density in air gap, that is in Tesla. Area of the coil, that is A. N number of turns, and I the current through the coil. These are instantaneous value of current. And one more thing, that damped oscillations is happening because of one more thing, that is the oscillatory nature of current as well, or the fluctuating nature of current as well. Okay, then the second one is the inertia torque, that is Tj, that is J d square theta by dt square, where J is the moment of inertia and theta is a deflection at any time t. And damping torque Td, that is d theta by dt, that is the damping constant, that is d is the damping constant. And then we have the controlling torque, that is given by Tc is equal to k theta, where k is the spring constant. These are very familiar terms that we have discussed in the first module itself. And we know what is the equation of motion, that is Td is equal to Tj plus Tc plus Td, because all the other torques will be opposing the driving torque. And we substitute the respective values against each of the torques, and we get equation number 1. And we know what is I. I is nothing but dq by dt, where q is the charge to be measured. And 1 becomes, if you substitute that, then instead of I, we can substitute dq by dt. And then we have to make that differential equation that is proper, that is by making the coefficient of d square by dt square 1. So what is the coefficient of d square theta by dt square? That is j. So divide throughout by j, and that is what is happening in equation number 2. Now, as I told that is during the time interval, let us assume that time interval is 0 to t1. So in that time interval, that is from 0 to t1, let us assume that the current changes and the flux linkages changes. So due to the large moment of inertia, only after this time interval, that is after t1, that there will be some changes, or there will be some throw, or there will be some deflection whatsoever in the galvanometer. That is due to the moment of inertia in the system, and that moment of inertia is deliberately done to achieve a point, that is the deflection should not happen, or the throw or swing of the galvanometer should not happen until the entire transitory nature of current has happened, or the entire flux linkages change has happened. So after this has happened, then there will be some deflection or throw or swing in the galvanometer. So let us assume that whatever changes are made in the current or flux linkages, let that happen in 0 to t1, so that after t1 there will be some deflection in the galvanometer. So that is what is elaborated there. That is, let the instant of time during which the charge q passes be defined as the time between t is equal to 0 and t is equal to t1. So integrating 2 with respect to time within limits t0 to t1. So we are integrating with respect to time within limits t0 to t1. And you know what is happening there. It's very easy to understand, and you'll get such an equation. Between this time interval, I told that in between 0 to t1, where there's a change in charge or change in current or change in flux linkages, there is no motion or there is no swing of the galvanometer. So theta can be taken as 0. Okay, let us see what happens then. So therefore the equation becomes d theta dt equal to q g by j. Why that is happening? Because theta is equal to 0. Now after passage of charge, so that equation changes to d theta by dt is equal to q g by j, because theta is equal to 0 in the time interval 0 to t1. So after passage of charge, that is after time interval t1, no current passes through the coil of the galvanometer, and hence Td is equal to 0. So when that happens, I is equal to 0, no charge, q is equal to 0, so the RHS is equal to 0. So the equation becomes j d square theta by dt square plus d theta dt plus k theta is equal to 0. And just take the term d square theta by dt square, and we know what is d theta by dt, that is equal to q j by g by j. So d square d square theta by dt square is equal to d by dt of d theta by dt, and instead of d theta by dt we can substitute g by j into q. So g by j will be coming outside. dq by dt is nothing but I is 0 after t1. So what happens to d square theta by dt square? That is equal to 0. So after t1 I is equal to 0. So what happens to the equation? Equation becomes d theta by dt plus k theta, that is equal to 0. That happens after t1. Okay, from here we know what is k theta. So what is k theta? K theta is equal to minus d theta by dt, or theta is equal to minus dg by kg into q. And you know that d is a constant, g is a constant, k is a constant, and j everything is constant. Only thing is that so that overall is a constant, so we can write it theta is directly proportional to q, that is charge is directly proportional to deflection at any point. You can see the graph there. The first swing is very important. So theta is nothing but theta 1. Whatever we want to record, that is theta 1. So theta 2, theta 3 all are that does not be recorded, but theta 1 should be recorded. And the first swing is very important. You may remember that while we discussed about the circuit regarding the BH curve and hysteresis loop, across the galvanometer, ballistic galvanometer, we had a key or a switch K represented by K. What was the purpose of that switch? See, I told that the first swing is the first swing that is happening in a galvanometer, that should be recorded. So here in this figure, that swing is theta 1. So theta 1 should be recorded. So how all other swings, maybe theta 2, theta 3, theta 4, all that can be neglected or simply disregarded. So how can you record the swing theta 1? After the first swing, you just close the switch K, so that you are shorting the galvanometer, or you're taking galvanometer out of the circuit. So after theta 1, or after the first swing or theta 1, you simply short circuit or take out ballistic galvanometer out of the circuit, because you need not record theta 2, theta 3 and theta 4 subsequent oscillations, even though they are there. Okay, so we are simply disregarding or neglecting such swings. So we only need theta 1 or the first swing, and for that, after recording that, we simply short that key, so that we'll take the galvanometer outside the circuit. So what we have done here is that we got theta d theta by dt from the assumption that theta is equal to 0 in the interval 0 to t1, and whatever deflection is happening in the galvanometer will happen after t1, and that is not due to what is happening at that time, but that deflection is due to whatever happened before t1. Okay, so whatever has happened for that deflection is happening only, it has happened before t1. So whatever deflection happening after t1 is happening is due to whatever happened, whatever circuit changes or whatever parameter changes that happened before t1. So that is why we considered 0 to t1, that in time interval t1 there is no motion theta 1. So that result is taken inside the case after t1. Okay, so that whatever be the deflection will be due to the changes that was made between 0 to t1. So that is the crux of that derivation. Okay, so we are taking two conditions, that is whatever is happening between 0 to t1, and what was happening was that at that point there was no deflection, so theta was taken as 0, so that we got the result d theta by dt equal to q g by j, and that result is substituted in the equation of motion, and which is happening after t1. So the equation of motion that we have written, that is after t1, is applicable after t1, and that is that whatever is that equation of motion is happening because of the things which happened before t1. So the result of 0 to t1 time interval is taken to the equation after t1. So that result is substituted and we get the deflection, and that deflection is directly proportional to q, and whatever be the changes in q is happening between 0 to t1, and that result is taken into the equation from after t1. Okay, so that we get the final result, and that's a very simple derivation, and you have to and read and understand. I'll be circulating this material after this video. So thank you so much.